momentum of the system. I have two parts of that system, mass number 1 and mass number 2. That initial momentum is equal to the final momentum. So I'll give you a couple minutes, and then I'll jump in. As we just came in, we're doing this problem 166. These are the values. 1 kilogram mass with a speed of 2, 2 kilogram mass with a speed of velocity of -4, and then the mass 2 has a final speed of -1, so it's to the left. And then I want to know what is the speed of m1. All right, so here I want to say P initial equals P final. I have to remember that these are vector quantities, okay? So my P initial includes the momentum of this particle plus the momentum of this particle. So those can be 1 times 2 plus 2 times -4. 1 times 2 plus 2 times -4. And then that's equal to the momentum of this particle, which is m1 v1f, plus m2, which was it 2 kilograms? 2 kilograms times -1. And then we solve for v1f. m1 here is 1 kilogram. So that's 3 minus 6 plus 2 equals v1f. It's negative, y'all got -1, is that right? Y'all got -1 as well? Did I do that right? Yes, okay. Y'all good on the 1D problems? We're going to do a couple more examples, so if you're not quite there, that's okay. But what we do is we set our initial momentum equal to our final momentum, calculate our initial, and then set that equal to our final, and then solve for whatever it is that we're looking for. Okay, let's try another problem. Can I go away from here, y'all? Yeah. What? The 3. Oh, yeah, I made a mistake. I'm sorry. Uh, this should be 2. 1 times 2 plus, oh shoot, this is all off, isn't it? Okay, I don't say anything. 2 minus 8 equals 1 v1f minus 2. So that's equal to -4 equals v1f. Is that right, y'all? Yes, okay. I don't like this 4-day weekend business. Do y'all like? I don't like the Monday, Tuesday. I think I'd rather have the Thursday, Friday break. It's hard coming back after on a Wednesday. Okay, let's try another problem. We're gonna watch a clip actually. This is from that movie Dodgeball, where this is y'all seen that movie Dodgeball? In the end, they have this scene where Peter LaFleur and White Goodman are facing off in this death match, this dodgeball death match. And so Peter LaFleur throws a ball. It's sort of this like very Matrix-esque scene. He throws a ball at White Goodman, and it knocks him back. And so we want to figure out what is the speed of the ball. So we'll look at that. Let's watch the clip first, and then we'll do some simple calculations with momentum. Remember, whenever you have a collision, momentum is conserved. So I know it seems like we're making uh, simplifications, but it still holds that momentum is conserved, and the values that we calculate are still real. This is how when they have collisions and car crashes and other types of collisions, it's how they determine the forces involved or the velocities of the objects involved that are involved in this collision. There are two objects involved. What are they? The ball and the guy, right. So we have this dodgeball traveling, and then we have the guy. Now, initially, the only thing that has momentum is the ball, because the initial momentum of this ball is equal to the mass of the ball times the velocity, and it has a certain velocity, but White-Goodman has a velocity equal to 0. So I'll call that VWG. I'll just call it VW initial for White-Goodman. And then the ball as it travels towards him. Now, in the final state, that's initial. In the final state, if you watch, the ball just sort of drops to the ground. So it's what do they call it? Dead ball? Is that what they call it? Where it doesn't bounce? Anyway, it doesn't move. But we do see White Goodman move. How far does he move back, roughly? You might want to venture a guess. He moves pretty far, right? 6, 7, 8, 9 feet even. We'll say, I'll just say 3 meters. So if he moves back a distance equal to 3 meters, and if you watch, he does it in a time equal to about 1 second. So his final velocity then is about 3 meters per second. This is the final velocity of White-Goodman. And the final velocity of the ball is equal to 0. All right, now we set the initial momentum equal to the final momentum. Ashley? The initial momentum is the mass of the ball times the velocity of the ball initially. And then the final state, because the velocity of the ball goes to 0, it's only the momentum of White-Goodman. So it's the mass of White-Goodman times his final velocity, which we said was 3 meters per second. Mass of the ball in grams is what, roughly? Is it a kilogram, a dodgeball? You ever felt a kilogram? Kilogram's pretty heavy, maybe a half a kilogram. So we'll say about 0.5 kilograms, 500 grams. It might be up to a kilogram. And then VBI, which is what we're looking for. Mass of White-Goodman-ish. What do y'all think? 10 kilograms? About 70. Or let's say White-Goodman, he's a pretty big guy. I mean, he's not tall, but he's stout. So we'll say maybe 100 kilograms. Makes our numbers easier. I say 100 kilograms, and then we've already said that this is 3 meters per second. And so now we can figure out the initial velocity of the ball is going to be 300 divided by a half by 0.5, and that's equal to 600 meters per second. So that ball is traveling at 600 meters per second. Just to give you some reference, muzzle velocity of like a pistol, a handgun, is about 300 meters per second. So twice the velocity of a bullet coming out of a handgun. That's pretty cool, no? That he can throw it that fast at 600 meters per second. Every second it travels 600 meters. Let's try a clicker question. It's the same question, just with different numbers. So y'all try this, and then we'll move on to 2D collisions. So here I want to know the final velocity of White-Goodman with sort of more typical velocities, 10 meters per second for the ball. What is the final velocity of White-Goodman? Free to ask your neighbor what they put. We're doing pretty well. Most of you, just a couple wrong answers out there. Let's stop at 115. 115. All right, good. A is right. We do the similar thing. The initial momentum is just the ball. Now remember, this is because the White Goodman's not moving. So we really have two objects with initial momentum, but one of those is zero. So I'm not writing the momentum of White Goodman in the initial state. So I would write mass of the ball, velocity of the ball, initial. Actually, I will go ahead and write that. Mass of White Goodman, velocity of White Goodman, initial, but this is equal to 0. And this has to equal to the mass of the ball, velocity of the ball final, but this is equal to 0, plus the mass of White Goodman, velocity of White Goodman final. And so I get 0.5 times 10 equal to 100 times V White Goodman final. And solving for that, I get a 0.05. That's 5 divided by 100, which is 0.05. All right, let's apply this now. Oh, why can your nose never be 12 inches long? Because then it'd be a foot. All right, let's do multidimensional collisions. This is what you'll have on the test, but it works exactly the same as 1D collisions. So if you know 1D collisions, you just got to throw in one little extra step, and then you'll be good to go for multidimensional collisions. We'll just do 2 dimensions, although it applies in 3 dimensions as well. So whenever I'm considering collisions in 2 or 3 dimensions, I say it's exactly the same, except I say that the momentum is conserved in all 3 spatial directions. So it would, for example, look like this. The mass of particle 1 times the velocity initial of particle 1 in the x direction. So I'll just add a little extra subscript there, plus the mass of particle 2, the velocity of particle 2 initial in the x direction, that's the x component. That's going to equal to the mass of particle 1, velocity of the particle 1 final in the x direction, plus the mass of particle 2, velocity of particle 2 final in the x direction. And then I can write similar expressions for y and z, that those will always be the same. My momentum in the x direction is always the same. My momentum in the y direction is always the same. And my momentum in the z direction is always the same. Let's work an example. Oh, I'm sorry, it's on the next page. I have 2 particles that collide, and I want to know what is their uh, the final speed of the first particle. You think? Listen, so the questions that you'll have are these. They're not going to be really any different from these, except they'll have different numbers. They have some homework problems, and you can look back at old tests, but don't expect any uh, vast differences from this, really just different numbers. So if you can work through a 2D collision like this, they don't really change very much, except for the values, the velocities that you're dealing with. But there's not much that you can do to change that up. Uh, so here I give the velocities in vector notation. You should know how to put velocities into vector notation like this, where you find the x component and the y component, but I'm not going to do that. You'll have the velocities as they're written here in this I, J, K vector notation. So you're not going to be dealing with K, but you can imagine that it's just one extra step if you are dealing with K. Okay, so here I have 2 particles that collide. Notice that one's moving in the x and the y directions, and then after it collides, it bounces off and moves also in the x and y direction. And I want to know what is the velocity of this second particle. So what I do here is I say, well, I want to work it this way, and I'll show you. There's another way you can do it, like where you separate your x and your y components, but we'll do that here. So I say that my initial momentum is equal to my final momentum. And my initial momentum is going to be that first particle is 2 kilograms. That's M1. V1 initial is 4I minus 1J plus M2, which is 4 kilograms. And V2I is minus 1 in the I direction. And then this is equal to 2 kilograms times negative 3I minus 2J. I have to be careful with my IJK notation, my vector notation, that I don't get it mixed up and I don't leave them off because they give you very valuable information. And then M2 was 4 kilograms times V2F. Now, I want to solve this for V2F in such a way that I retain the vector information. So what I'm going to do is I'll group my I terms together and group my J terms together. And then that'll be my solution for V2F. You have extra space on the next page, but I'm just going to do it here. Or you can do it here too if you like. So I have 8I minus 1J, or excuse me, minus 2J. Just distribute this 2 here, plus negative 4I, distributed that 4 there, is equal to negative 6I minus 4J plus 4V2F. And then you solve that for V2F. I'll give you just a second to solve this now for V2F, but keeping it in I and J notation. So don't get rid of those I's and J's. Just keep them and join up like terms. I get 2.5I plus 0.5J. Is that right? Did I do that correctly? Is that what you got? Okay, thank you, Josh. So 2.5, 2.5I plus 0.5J. And that's the answer. Okay? That's all it is for 2D collisions. Momentum, I find that momentum is pretty easy to deal with, and that's what makes it a very valuable tool when you're looking at collisions between particles, that there just aren't really a lot of problems to deal with. Your momentum's always conserved. It doesn't matter what kind of forces are involved. Um, and when you break it into vector notation like this, it can be fairly straightforward to deal with. Students usually do well on this problem, so make sure that's your, goodness, bless you. Make sure that you get the full credit on this problem. It should be a problem that you're able to just do quickly and not have any issues with. But make sure that you practice. You'll need to practice it a couple times. Okay, folks? Likely to be on the test. All right. Why don't y'all try this one? This came from a test just for a little extra practice. Two particles collide. What is the final velocity of M1, that first particle, that 2 kilogram particle? Notice you'll just have one momentum term to start because this M2 is initially at 0, so it has no momentum at all. All right, folks, your initial setup should look something like this. My only particle that has an initial momentum is P1 because P1 is the only one that's moving. P2 is initially stationary. I think I know, is it the final velocity of M1 that I know? It was given 0.5. Yeah, so I'm looking for V2F. Uh, V1F is given right here in the problem. So it's going to look like this. I'll have 2 kilograms times 3I minus 4J equal to uh, 2 kilograms times V1F, that's what I want to know, plus 4 kilograms times zero point 0.5, what is that, IJ or K? It's I, because it's in the positive X direction, and so it's positive I. And then I solve for V1F. I get 6 minus 8, oops, excuse me, 6I minus 8J. You can think of these vectors I, J, and K. They're not really, but you can think of them as variables like X, Y, and Z. And then as you're going through your algebra, just treat them like that. Now, they're not variables because they have a known magnitude, 1, and they have a known direction in the X, Y, or Z directions. But you can think of them that way. Equals 2 V1F, and then 4 times zero point 0.5 is 2. Am I missing something there? No, that's right. And then I have 4I minus 8J divided by 2 equals V1F, so that's 2I minus 4J. Okay? We'll have one more practice before we wrap up today for you to try this out. We have one other type of collision. Okay, you'll need to know the different kinds of collisions. There are two different kinds of collisions that you need to know, and those are elastic and inelastic collisions. Elastic collisions, energy and momentum are conserved. These are very special collisions. They don't happen very often. Uh, if we think about two cars crashing into one another, is energy conserved in that collision? Is energy conserved in a car crash? No, you lose all sorts of energy in a car crash because, first of all, the main thing is that the cars just crumple. The bumpers will crumple, the hood will buck up. So that takes a lot of energy to deform those materials, and that's called lost energy because it's energy that can't be used again. Uh, You also lose energy to thermal energy, sound. You lose lots of stuff in a collision like that. There's only really a couple of examples where energy is conserved, really only one that I can imagine. What kind of forces have to be involved for energy to be conserved? We talked about these forces back in the previous chapter. What kind of forces conserve energy? No, not spring. We sometimes approximate a spring. Gravitational is a type of force that conserves energy. There were a couple of others, but a particular type of force What is gravitational force? It's a what type of force? It's a field force. Field forces are conservative forces, and only conservative forces conserve energy. So anytime I have contact between two objects, I'm losing energy. So in order to conserve energy, I have to have a force that acts over a distance, that doesn't require contact between two surfaces. Um, so aren't many examples of this? Can y'all think of one example of a conservative, a collision that involves conserving energy? When you're a chemist, what is it? It's the collision between molecules and atoms, charged molecules and atoms, because they never actually touch one another. They'll come close to one another, and then because they have these charges, they'll repel one another. If I have two positively charged particles, they'll repel one another and have a collision, but they never actually touch. So, an example of this is the collision between charged particles, or molecules, atoms, ions. We can also approximate some collisions as elastic, and we do this even though they're not truly elastic, such as, for example, billiard balls. And we can think of other collisions that we can approximate that they just don't lose very much energy. But really, the only truly elastic collision is between charged particles. And so, elastic collisions, only momentum is conserved, uh, and energy is not conserved. This involves every other collision in the universe. So practically every collision in the universe is inelastic with a few exceptions, meaning the collisions between charged particles. All right, let's try. There is also a special case of an inelastic. Does inelastic conserve energy, momentum, or both? The inelastic. Momentum, only momentum. That's right, not energy. Oh, and by the way, I like to think of this as like a bouncy ball. If I have a bouncy ball that's really, really bouncy and I drop it, it's very elastic, right? A very bouncy ball is very elastic. If I drop it, what will happen to it? How high will it come back up? Almost all the way, right? And so I think of that as an elastic collision because it's a very elastic ball and it's conserved most of its energy. Whereas if I have an old tennis ball or another ball that's just not very good anymore, it's not very bouncy, it's not very elastic. If I drop that ball, what will happen to it? Will it come up all the way back up to my hand? No, I just sort of, maybe come up halfway or so. So if that helps you remember elastic and inelastic, that's great. If not, that's fine either way. But just remember elastic collisions conserve energy, inelastic do not conserve energy. This is a special case of an inelastic collision. You'll work it exactly the same way as you did the others, where after my two particles collide, they stick together. And this actually happens a lot more than you would think. Go outside and start looking around and think about, gosh, is this an elastic collision? Or excuse me, is it a inelastic collision or a perfectly inelastic collision? Perfectly inelastic is just where they stick together. So like for example, a car, if it's traveling along and it runs into a garbage can or whatever, and they stick together, they continue moving at the same speed, that would be a perfectly inelastic collision. You ever done that? Run into garbage cans? No, my brother, listen, my brother's awesome. You'd love him. But when he was a teenager, he got into a lot of trouble. Both my brothers did, actually. And one night, I remember him going out and in his truck, and he just went out and ran into everybody's garbage can. Because he was kind of, I don't know, he thought it was fun. I mean, I'm sure the people didn't think it was much fun, but he thought it was fun. One time, my other brother, this is going to kind of gross you out, but he climbed up the water tower. And first he did graffiti. Moondog was his name. He graffitied that on the side of the thing, and then he peed into the water tower. He thought it was funny. I'm sure nobody else thought it was funny, but isn't that terrible? Anyway, so inelastic collisions. Um, The objects stick together upon colliding, and so they both have the same velocity. Otherwise, you work it exactly the same way. All right? It actually is quite a bit easier because what you would have here, let's just give them some speeds. We'll do a 1D problem. Let's say that V1I is equal to 3 meters per second. V2I is minus 1 meter per second, because it's to the left. Let's say that this is 2 kilograms and this is 4 kilograms. And I want to know what is V2F. Right, just like we've been doing, I say the initial momentum, that's 2 times 3 plus 4 times negative 1. That's equal to the final momentum, which is going to be 2 plus 4 times Vf. Since these both are sticking together and they're moving off in the same direction at the same pace, I can just figure out those masses, what's that called? Factor out those masses and multiply times Vf, because they both have the same speed, the same velocity. So that's 6 minus 4 is 2 divided by 6 equals Vf. All right? So don't be thrown off if you get a perfectly inelastic collision. It works exactly the same. In fact, it works out a little easier than some of the others because you don't have to deal with that V1F, V2F, that you only have one VF in the end. In these, momentum is conserved, energy is not conserved. Right, let's try this quick test. This is from an old test. This is a 2D collision, but you work it exactly the same as you did the others. So you keep your I's and your J's separate. Your setup should look something like this. This is the initial momentum of the first particle, initial momentum of the second particle. I combine the two masses because they're going to be moving at the same velocity. So I just say 2 plus 4, and then I multiply that times Vf. And now I solve that for Vf, keeping my vector notation. That's 8I minus 2j minus 4I divided by 6. 2/3 I minus 1/3 j. What I get? Is that true? Is that correct? Yeah, awesome. Okay, so you could have a 2D perfectly inelastic collision. You wouldn't have both. You wouldn't have an inelastic collision where they go off in different directions and a perfectly inelastic collision, but you could see either one of those on your test. Hopefully that's an easy 10 points for you. Just practice a little bit, okay? Look at the old test, maybe work through one on your own, completely on your own, and then see if you get it right. If you do, move aside and look at some of the other stuff, which can be more difficult. All right, let's look at one more type of problem. You should have a blank page on 176. I'm going to put it there. That is an elastic collision. Remember, in elastic collisions, energy and momentum are conserved. All right, so let's say that I have two particles. I have a 1 kilogram particle moving at 2 meters per second, and it collides with an elastic collision with a second particle that is 2 kilograms, and its initial speed, v2 initial, is equal to 0. This is v1 initial is equal to 2 meters per second. And now I want to know what are the speeds, the final speeds of both of these particles. This is one-dimensional. You're not going to have an elastic collision in 2 dimensions, but the same still holds. It's just the equations get a lot more complicated. This is different from our previous problems because in the previous problems, I gave you one of the final speeds. And so you can't just look at the momentum and solve this because you'd only have one equation and 2 unknowns, and you can't solve that. But because it's a perfectly elastic collision, or not perfectly elastic, because it's an elastic collision, not only is momentum conserved, but energy is conserved. So I'm going to have one equation for momentum, and then my second equation will come in how? What's the second equation going to be? I do the conservation momentum, and then I do conservation of what? Energy. So you just have two equations, one from conservation momentum and one from conservation of energy. And they'll look like this. I say M1 V1I plus M2 V2I, though I know that's 0 because its speed is 0, equals M1 V1F plus M2 V2F. We just underline my unknowns. I don't know that, and I don't know that. So I can't solve that equation. But I also know that 1/2 M1 V1I squared plus 1/2 M2 V2I squared is equal to 1/2 M1 V1F squared plus 1/2 M2 V2F squared. So now I have two unknowns, two equations. These are two independent equations, so I can solve them for those two unknowns. Okay? So I'm going to do this. Well, first, let's just simplify it because some of these things go away. In fact, I gave you these numbers because they work out easier than they would otherwise. So this whole term goes away, as well as this whole term goes away. I can also just divide by 1/2 on all of these. So I can get rid of the halves here, here, and here. I just divide through by 1/2. And then that gets rid of that 1/2 on both sides. And then that's it. Now I want to know, I'm going to have to solve one equation for one unknown and plug that into another. And so the way I did it, there are a couple ways that you can do this. But the way that I did it is I solved this equation for V1F. And it's equal to M1 V1 initial minus M2 V2F divided by M1. And then I'll go ahead and put in our values there. I get 1 times 2 minus 2 V2F divided by 1. So it's 2 minus 2 V2F. Now I plug that in for V1F here. And I can solve that equation then for V2F. So I come here. What I'm doing here is I'm taking this and substituting it in right here for V1F squared. I'm just going to set it up for y'all, and then I'll let you solve it on your own. It's solving an equation for a single variable. So it's going to look like this. M1 which was one, I'm going to go ahead and put in values here, 1 kilogram times V1 initial, which was 2 meters per second, squared, that's this part, is equal to M1, which is 1 kilogram times 2 minus 2 V2F squared, that's this term, plus M2, which is 2 kilograms, times V2F squared. The 1 kilogram is the mass of particle 1. So I'm just rewriting this equation right here, and I'm putting in our known values. So M1 is 1 kilogram, V1 initial is 2 meters per second, M1 here is 1 kilogram, V1F, which I don't know what it is, I have to substitute this in, and then I have M2, which is 2 kilograms right here, and then V2F squared, which is just pulled down. Now notice here I only have one unknown in this equation, and I can solve that for V2F. All right? Usually I give this as a take-home before the exam because the algebra gets a little hairy when, even if you have a simple one like this where the numbers, you'll see as you work through it. Let me go ahead and give you the answers. V2F is equal to 4/3. Actually, you'll get two solutions for V2F. You'll find that it's either 0 or 4/3, but we know that it can't be 0, that it's not going to not move because it's colliding with this object. So you'll also get a solution of 0 when you work through the algebra of this. And then V1F is equal to minus 2/3 meters per second. Once you find V2F, you plug it in here to get V1F. All right? Later in the week, let's see, on Friday, I guess, I'll bring you this, or I'll email it to you, a PDF of, just a second, Katarine. I'll email you a document with the take-home problem for this, okay? Just because solving this, it takes too long, and people usually make mistakes, and it's hard to grade. But I do have a much higher standard for our take-home. Like, I expect it to be perfect. I expect you to have the right answer and to show all your work. Now, you can use any resource that you want. I even allow you if you like to work together. So just make sure that it's right. Okay? Katarine? I'm sorry? Minus 2/3. And it'll just be in one dimension. Y'all could do this. It's really just algebra, solving the algebra. But you set your energies equal, and you set your momenta equal to one another. Okay? I'm not sure how many points it'll be, 10 or 15 or so for take home. We'll have another take home in the next, not this coming chapter, but the next chapter. So as we get into sort of more complicated problems, you'll have more take home assignments for exams. That's good for y'all, right? It's a good thing? Yeah. Any questions, y'all? Let's do a few clicker questions. We'll wrap up this chapter. How far had we gotten in the concept tests? Had we finished them? We had started them, right? Where were we? 6.26. Oh, not very far, huh? Okay, two objects are known to have the same momentum. Do they necessarily have the same kinetic energy? Yes or no? All right, let's stop at 25. them? Not necessarily, because if they have the same momentum, they could have different masses and different velocities, but still have the same um, momentum. But if they have different masses and velocities, since the kinetic energy is 1/2 mv squared, then they won't necessarily have the same energy. It's because of that v squared term. Hey, what do you get when you divide the circumference of a pumpkin by its diameter? And you say, I don't know. Pumpkin pie. All right, a net force acts on a 100-kilogram boulder and the same force on a 130-gram pebble. How does the rate of change of the boulder's momentum compare to the rate of change of the pebble's momentum? Let's stop at 45, 45. All right, the answer here is C. Remember, this goes back to Newton's second law. F, this came early in chapter 6. F is equal to dp dt, or we can write it not in differential form as delta p over delta t. So if I have a force that acts on a particle, it causes the momentum to change over a certain time interval. So if I have 200 newtons acting on one object and then also on another object, if they happen over the same time, which we assume they do, then you're going to get the same change in momentum. A same force will give you the same change in momentum. Doesn't mean they're going to be traveling at the same speed, but they'll have the same momentum. So C is the right answer here. Now, how does the boulder's velocity, rate of change of velocity, compare to the rate of change of the pebble's velocity? All right, we'll stop at 38. Okay, that's right. B is right. And we'll stop there. Y'all have a great day, okay? It just has a higher mass, F equals ma. If m is big, a is small. Yeah.